Hi everyone, today I would like to present the BioMems project. On this project, I will focus on molecular biology on the chip, the importance of point-of-care diagnostics. As you know, the class already mentioned about the cost is very high in the point-of-care diagnostics. And this work will describe an integrated PCR system that performs automated sample preparation and fast polymerase chain reaction. As you know, PCR for a form ligation in point-of-care testing. Beyond the paper, integrate automated fast PCR system for point-of-care molecular diagnosis of bacterial infection. In a centralized laboratory, the first step for the sample of blood is usually a centrifugate, in which the plasma is separated for further study from a cellular component. So this system is assembled from inexpensive 3D printed parts aimed to reduce the cost and focusing on the ability of performing automated DNA sample preparation, including step extraction, separation, and purification of DNA from the centrifugated plasma. Also, the variance of the automated sample were clearly lower than the achieved using manual DNA extraction. And after describing the paper system, I will suggest an idea with a modification on the side to improve this system. So, the automated fast PCR system as in Figure 1 were fabricated from 3D printer parts, commercial electric element, and the motor. The system in Figure 1A have two-axis translation state. So, and after that, and next, two servo motors were implemented to separately move a magnetic bar and magnetic cover in the Z-axis direction. A magnetic bar and the temperature sensor were fixed at the end of the tip in servo motor 1. A magnetic plastic cover were mounted on servo motor 2. The figure B is the sample cartridge holder with cross-section view, and I will focus on the sample cartridge of automated DNA extraction. The figure C is the photograph of automated fast PCR system for whole system here. As this is the paper, you can see how it's step by step the system is working. The first, for the cell separation, they will use the similar nail cell and lacking on the reagent in the right chamber and run the system. So, as shown in the figure 2, the automated extraction process basically follow the manual protocol. The system was designed to have 4 valves containing lysis buffer, washing 1, washing 2, and elution buffer. The magnetic strip were mounted on the end of servo motor 1, and the magnetic cover were mounted at the end of the servo motor 2, as you can see in figure 2a. The workflow for mixing, capturing, transport, and dispersion were automated, as you can see the follow in figure 2b. Firstly, the target sample were mixed with lysis lesion solution in the first well, and after that, the magnet cover can be moved up and down by servo motor 2 and be quickly shifted from the side to side by the step motor for mixing and magnetic particle dispersion. Then the magnetic particle with extracted DNA were collected by the magnetic tip, transported to the washing chamber, washed, and redispensed in the solution by mixing without the magnetic tip. Finally, the extracted DNA were released in the elution buffer as you see in the figure 2C. The magnetic particle transport and redirection to the next well in 10-0 step. A magnetic cover state G2 will move down. Then the magnetic tip state in G1 will move down together. When magnetic particles with DNA were collected by the magnetic tip, only G2 move up. When the G-axis state transport to the next well, the G1 will move up after only G2 move down. Then the magnetic particle can be redispersed into the washing solution of the next well. The total time to require for the ultimate DNA extraction is about 5 minutes, due to the rapid seeking mix without turnaround time. However, manual extraction takes about 20 minutes due to a longer mixing and waiting time between each step. So this can be dramatically increased if the large number of the sample must be prepared. So for the application here, the DNA was extracted by both the automated and manual methods. The initial concentration and purity of the extracted DNA from the automated and manual methods were measured in using a spectrophotometer, as you can see in figure 3A on the right side. And as 108 CFU per milliliter salmonella, the concentration were about 20 nanogram per microliter, with purity of 1.68 by the manual method, and about 20 nano per milliliter with purity of 1.66 for DNA by the automated method. So the manual method achieved a higher average DNA concentration and purity than the automated system did. But measurement by the manual method also had 3 times higher standard deviation in purity and 10 times higher standard deviation in concentration than the automated method. To confirm the efficiency of DNA extraction by the manual and automated methods, PCR amplification detection of the sample were carried using the commercial PCR device. The real-time curve, as figure 3b shows, increased faster for the manually treated sample than for the automated method. The manually treated sample have the circle threshold about 17, and the automatically treated sample has the cycle threshold about 18.3. However, the circle threshold deviations of the manual extraction sample were 4 times larger than those of the automated extraction sample. This result means that the automatic extraction is more reproducible and reliable than manual extraction. While the reverse presentation device shows rich promise, but it still has the limited in using the centrifugated sample in the plasma. It means they need the centrifugation machine to prepare the sample before using. So to fill out the bunk machine, that I suggest using the dead chain to enhance the erythrocyte deposition. It means check out the red blood cell outside the blood sample. So the figure 4a shows a schematic of the step in the process performance on a new design chip by myself. The first step, the dead chain and the blood will mix together and do the sedimentation. After that, the pushes plunger count an enriching positive pressure between the sedimentation chamber, the below plunger in the figure 4A1, and the chamber inside the plunger, upper plunger in the figure 4A12. thereby filtering only the plasma through the filter port, as shown in the solid row in figure 4a2. Then the DNA is collected by collection tip and moved to other temple until they release related DNA in the elution buffer as the same principle. The new thing is the check valve. The check valve is designed to allow the extracted plasma to travel from the sedimentation chamber upwards to the plunger chamber when applied pressure is positive, and to prevent the backflow when applied pressure is negative. The check valve consists of an exchange hole on the polydimethylsiloxane, I call this BDMS, the laser bonded on the silicone ring. This elastomeric part rests on the sixth one, which is the position of the outer plunger part, and were fixed by bottom side of the inner plunger as outlet hole position. You can see in detail in figure 4b. The working principle of the check valve depicted in figure 4c include up three stages. Stage 1 is the normal position of the elastomer when the solution was just locked. The liquid in the plunger chamber and in the sedimentation chamber is distinguished. The stage 2 is open stage. When the applied pressure is positive, the check valve allows the liquid to pass through from the bottom up. Stage 3 is closing stage. When the applied pressure is negative, the check valve keeps the liquid separate in the upper and lower chamber. So if when I apply the new design in the same process, I can work from the whole blood sample. So I will remove the centrifugation machine. That's my suggestion for this work. Thank you.